Okay, so let us now see example 21. So it shows some functions and we will see whether the function is bijective or not. So let f be a function from the set 0, 1, 2 into the set consisting of 3 and 4. Be the function and it's defined like this. The value of f at 0 is 3. The value of f at 1 is defined to be again 3. And the value of f at 2 is defined to be equal to 4. Okay, then f is not bijective because both 1 and not 1 and 2, 0 and 1 in the domain get mapped onto the same element 3. Get mapped onto the same element 3 in the range. And this is a failure of injectivity, because what injectivity says is that if the function has to be injective, then distinct elements in the domain should have distinct images. However, they should be associated to distinct elements in the range. However, here 0 and 1 are mapped onto or associated to the same element 3 in the range. So that's why it's not injective, and as a result it's not bijective, because bijection is both an injective function and surjective function. It has to be both. So in bracket we can write, this is a failure of injectivity. So that's why this function fails to be bijective. Now we take another function. Now let G be a function from this set into this set. Be the function and it's defined like this. It has to be defined only on at 2 points, 0 and 1, because they are the only points in the domain. So G of 0 is, we can define it any way we want, but let's write it, what he has written, what Tao has written in the example. G of 0 is defined to be 2 and G of 1 is defined to be 3. G is also not bijective because for the element 4 in the range, there is no element x in the domain such that g of x is equal to 4. So that means this is not surjective. This function is not surjective. In a surjective function, every element in the range should come as an output of some element in the domain. That is not happening here for this particular element. So G fails to be surjective, and that's why it's not bijective. So this is a failure of surjectivity. So that's why G also is not bijective. Then finally we take another example. Next, let H be a function defined from 0, 1, 2 into the set 3, 4, 5 be the function that is given like this. Yes, h of 0 is 3, h of 1 is 4, and h of 2 is 5. The function h is bijective. H is bijective because it's both injective and surjective. This can be easily seen. Okay. Then we see the next example. Next, there is one more example. Example 3.3.22. So what this one says, this is again another example of a bijective function. The function, let me write it here, f from the set of natural numbers into the set of natural numbers from which we have removed 0, and the function is nothing but the increment function, is a bijective function. And the fact that this is a bijective function, it follows from these things. In fact, this is equivalent to axioms, Peano axioms 2.2, 2.3 and 2.4 and lemma 2 to 10. Axiom 2.2, okay, first of all, what does Axiom 2.2 say? It says that Axiom 2.1, of course, is the statement that 0 is a natural number. Axiom 2.2 says that for every natural number n, there is a successor, n++, the next one. So This, because of axiom 2.2, this is a well-defined function first of all. What does axiom 2.3 say? Axiom 2.3 says that 0 is not the successor of any natural number. That means 0 cannot appear here as an output. That's why this f is a function from n into n minus 0. Because we don't have 0 as an output, so all the outputs belong to this set. So now there is no problem. Because of these two axioms, we now have a well-defined function. And what about axiom 2.4? It says that distinct natural numbers have distinct successors. That means if I take two natural numbers n1 and n2 which are distinct, then axiom 2.4 says that the successor of n1 and the successor of n2 are also distinct. So essentially it just simply says that this function is injective. Okay, so that's how we are getting injectivity. And in lemma 2 to 10, we have the statement that every positive natural number is the successor of exactly one natural number. If I have a positive natural number A, then it is the successor of exactly one natural number B. So from this, we get the fact that f is surjective. So that's how f is a bijective function. Okay, so this is another example of a bijection. On the other hand, the function g, which is defined from n into n. Now we are not removing 0 from the range. The assignment of the elements is same is not a bijection. And why it's not a bijection? Because of this axiom 2.3, because according to axiom 2.3, the element 0, because now you see we have not removed 0 from the range, so we have 0 in the range, because for what am I writing? Because according to the element 0 in the range is not the output of G for any input x in n. That is, there is no x in n for which gx is equal to 0. Okay, and that's what axiom 2.3 is. That's what it says. So this is not a bijection. Okay, so there is a remark at the end. So the notion of a bijection not only depends on what the function does but also on its domain and range. The notion of an injective function depends on the domain. The notion of a surjective function depends on the range. The notion of a bijective function depends on both. Then there is a remark. This is 3.3.23. And what this remark says something about bijective functions. If a function that maps the element x onto fx, that is if f is the function, is bijective, we also sometimes say that f is a one-to-one correspondence and this should not be confused with one-to-one mapping. One-to-one mapping is an injective function. A one-to-one correspondence is a bijective function. Not to be confused with a one-to-one function. One-to-one correspondence or a perfect matching although this perfect matching, this term is used usually used in graph theory, but same thing actually. And yes, and we denote the action of f on x by writing this double, both ways we have arrow in both the directions instead of this ordinary function. Any function has a unidirectional character, domain, range, but bijective functions have both the directions. Exactly why, that we will understand soon when we get the notion of an invertible. Actually we have said what bijective or invertible function is, but when we get the notion of an inverse of a bijection, then we will understand that we can actually come back also from the range to the domain. This is coming soon. Actually that's the end of the text. So that's the same thing. The function h in this example that we have already seen, not this one but the previous one, h in example 3.3.21 is the one-to-one correspondence what was it? 0, 1, 2 and 3, 4, 5, yes. And lastly, there is one more remark. And this remark involves the definition of bijective function itself, and a common error or people get confused about the definition. And what Tao says is this: common error is to say that a function f with domain x and range y is a bijective function if for every x belonging to x there exists exactly one y belonging to y such that this or in terms of correspondence, no, in terms of function itself, such that y is equal to fx. But this is not the definition of a bijective function. This is not what it means for f to be bijective. Rather, it means f is a function. This is not the definition of a bijective function, but this is the definition of a function. In a function, for every x in the domain, there exists exactly one y in the range to which x is associated by the function. However, if you change the order of these two parts of this line, then that will be a bijective function. For every y belonging to y, there exists exactly one x belonging to x such that y is equal to fx, then that will be the definition of a bijective function. Why? You see, suppose this is your domain x, this is y. If we are saying that for every x in x, there is exactly one y in y such that f maps x onto y, then that's the definition of a function. But if we are saying that for every y in y, there exists exactly one x in x such that y is equal to fx, then this is not what I have just said now. This means that if I am arbitrarily choosing y, then there is exactly one x. First of all, there is an x for which y is equal to fx, which means that no element in the range will remain alone or remain unconnected. What that says is that f is onto or surjective. But we are also saying that for every y, not only is there an x, but that x exactly one x, that x is unique. So that means I will never have a situation like this where a single y is associated to more than one x, because for that y there is exactly one x. So that makes the function f injective or one-to-one. So that's how this becomes a bijection. But in this fashion, this is not the definition of a bijection, it's just the definition of a function. And then he continues, a function cannot map a single element of the domain onto more than one element of the range, because if it does that, then it's not a function at all to begin with. For example, f and g in example 3.3.21. I mean the first two functions which failed to be bijective, that example, are not bijective but nevertheless they are legitimate functions okay. And now comes the last part of this text, the text part of this section, and that is the notion of an inverse function. Let f from x to y be bijective. Let y be any element in the range. Let y belonging to y be any element, since f is surjective. Bijective means it has to be surjective as well as injective. We are using the surjectivity first. Since f is surjective, there exists an element x in the domain such that y is equal to fx. Now we impose the injectivity condition on f and see what it says. Since f is also injective, this x is unique, because for a given y I cannot have more than one x, otherwise it will not be injective by definition. So the x that has been determined from the choice of y is unique actually. Hence, we can define a function with domain y and range x that maps every y belonging to y to that element x belonging to x such that y is equal to fx. And now see, the condition for a function is actually true here. We choose any y belonging to y, there will be an x in x for which this is true. Why? Because f is onto or surjective, and that x will be unique because f is injective. So that means for every y in y there exists a unique x in x which we can find and which satisfies this equation. So we have now obtained a function with domain y and range x, the exact opposite thing. This function is called the inverse function or the inverse of x, and is denoted by f inverse. So f inverse maps y into x, and for any x belonging to x, comma y belonging to y, f inverse y is equal to x if and only if y is equal to fx. So this is the relationship between a function, a bijective function, and its inverse. Note one more thing, that this function can only be defined when our original function f is bijective. If f fails to be, say, surjective, then there will be at least one y in y for which we will not be able to find any x. So we cannot define the function. If f is not injective, then there will be at least one y in y which will be associated to more than one x. In that case also we cannot define a function like this. So only for bijective functions this inverse exists, and that's why bijective functions are also called invertible. They can be inverted in this way. So here the section ends, the text part ends, and now the exercises will start. So we now start the exercises. So this is the first one.